My name is Joseph Wunderlich. I'm a professor of engineering, architecture, and computer science at Elizabethtown College for 23 years, teaching this course every year. So computer architecture, high-tech fundamentals. So this has just been updated now, and there's 40 parts to this. Now on YouTube is everything except for this first part here. Note videos reviewed in 1 to 4 above the reviewed in these these videos review these things above here. I'm not going to go through that now. And then there's numbers 5 and 6 were part of a homework assignment and class discussion. And then we did these two, and I'm going to do this one right now, which is a continuation of things the students learned in this presentation here, but it goes a little more in depth into the paper. And then I'll come back and make links here. These are all on the YouTube channel, everything. And we'll look at that in a minute here. Well, I can just show it real quick. So I've reorganized the YouTube channel. I've made a separate play group for this course. Playlist, play group. So playlist. And now it's called Intro High-Tech Lectures, and all the other stuff's over in advanced and stuff. And so that looks like this. And there are 32 videos in here now. So I don't have all 40 on here. Some of them are in other places on my website. There's 270 videos up here now. And some of them I've got to move around. But so, and they'll all be in line very soon. I just finished loading them up this morning. They're pretty much in sequence, like you would see in the syllabus, and they will be by next class. Let's go back to the syllabus. Now. Okay, so we're going in here now. We're making right now this MP4 in YouTube. The MP4s are on the college web server in YouTube. So this is a paper I wrote when I was at Purdue University, and I used pieces of it in different courses here. And I have very little overlap in between my courses, and when I do, I clearly identify it. So this course, the highlighted parts are what students watching this right now should know in the 230 class, EGR 230, CS 230. So microprocessors versus microcontrollers. A microprocessor typically is either Intel or Motorola. It's the same for microcontrollers. There's whole families of them. Now, until the recent decades, Motorola was much more of a competitor in the microprocessor market. Now there's other contenders we need to talk about too, AMD and everything. So, but this is a pretty popular paper. It's been referenced a lot, and just add a couple new things in there. It's still relevant, the concepts. Now I talked about this with the students, and they need to know this. I didn't highlight the whole thing here, but it's highlighted in the presentation before, so they need to memorize that whole minimal computer architecture, which applies to all computing. I made this to do that, so the basic idea of how it works. And I'm not going to repeat that here. The previous talk did that with the students. Also, whether instruction code is stored in internal chip or external off-chip ROM or RAM, it must be fetched via a data bus, or a data bus after being pointed to by a program counter, which puts a memory address on the address bus. So talking about similarities. So we always have that fetch, decode, execute thing in any kind of processing. Now there's ASICs now, and there's ways of doing things with FPGAs and all kinds of things where you avoid that whole instruction sequence, instruction cycle, pipeline stages. You can actually write code now and embed the behavior of the code directly into FPGAs. And so people like it for that, those kind of things for that reason. But actual processor, you know, that it's general purpose and fully functional needs to have a pipeline, parallel pipelines now, multiple cores. And this is the basic idea here. The difference between microprocessors and microcontrollers. Typically, microprocessors, all memory is located off chip, with exception of some caches. But now all the caches have been integrated into the chips too. For a while, the L1s, only L1 was on the chip, and L2s and 3s are on somewhere, typically on motherboard and a PC between the processor and the memory. And the ROMs used to permanently store instructions such as bootstrap, you can find, and RAM used to store both data and other instructions. So that's the von Neumann-Princeton architecture, where you mix everything together in typical microprocessors. For many microcontrollers, there is a ROM and a RAM on the chip. Address space for additional ROM and RAM you can do externally. And the biggest difference is really that here, the instructions and data are stored separately. That's a Harvard architecture. And the ROMs usually contain all instructions after code development. And then the RAM is used to store data. So for embedded systems that just repeat the same code execution all the time, but the data changes, whether it's a fuel injector, or refrigerator, or air conditioning unit, dishwasher, lots of things now, billions of things, billions and billions of things actually use microcontrollers. So that microprocessors have caches for speeding up things. And we talked about that in the last lecture. I'm not going to talk about that here. And we have a whole lecture on cache. Just an introductory lecture, and then you'll see a note in the flow on the outline for the course next to the link for the cache. It's an introductory. One student here has already had the advanced class, and they can attest to the fact that we do more advanced cache design in there. And here it's just superficial. Get the idea of how it works, locality of reference, spatial and temporal locality of reference. That's about it. Whereas we design full caches on different mapping techniques in the advanced class. You know, they both have a program counter. You know, they both but both microprocessors and microcontrollers have a program counter to address instructions to be fetched from memory. However, calculations of instructions can be significantly more complex with a microprocessor, with target addresses of branch instructions being prefetched using the branch prediction strategies. I did some of this at IBM, and with several levels of address translations to get the real address. So this class, we've already talked about this a little. I can talk about it here again real quickly. You have virtual addressing in microprocessors, where you can have 2 to the 64 of an address space, the operating system and all the applications developed for that processor, and systems and application level code thinks, and is given the opportunity to think it has 2 to the 64 of space, which is huge, right? Because 2 to the 30 is a billion, and so 2 to the 60 is a billion billions, and it's 2 to the 4 there too. So 2 to 64. So you have ridiculous amounts of address space with 2 to the 64. That's why you only have 40 pins actually coming out of your processor on the typical Pentiums on motherboard, because 2 to the 40 is plenty. That's a terabyte. That's 2 to the 10 times. It's 2 to the 10 gigs, essentially a terabyte of RAM, and we're not there yet. But even if we're getting close, you don't need more than 40 pins. And so you have to translate every address. Every time you address memory, you have to translate that. And then beyond that, cache those translations. So talked about that before in here. We've talked about it twice. Last time, or in the talk, the presentation that preceded this, we went into this. This is a very important equation. I'm not going to drill down into all of it, other than to say that the time it execute a task is a function of how fast it switches, which is up to the device physicist, how many lines of code, which is all the coders that use it, and plus what kind of software you use too, And then most importantly, the average cycles per instruction, if you're a hardware designer, where you speed up the machine by doing a million different things, well, not a million different things, but a lot of different things in parallel pipelines, any kind of caching, regular caches, data instruction, caching and branch predictions, which we just talked about, caching virtual translations. All that is speed up measures that reduce the average number of cycles, decrease the average number of cycles per instruction. Microprocessors are much better suited for number crunching. We're going to talk about floating point in detail coming up here, and you'll appreciate that. The complexity of processing floating point is compared to integers, whereas microcontrollers are typically in just integers. Microprocessors are much better suited for number crunching and usually have a wider data path and larger general purpose registers to accommodate this. Microcontrollers are typically limited to 8 or 16-bit number representations. Well, 32s now are common. I wrote this paper in '99, and so you can just bump up any little number here. The principles stay the same. And then these number ranges, we have a whole talk I'm going to do on number representation as well as character representation. We'll talk about ASCII, actually EBCDIC too, which probably none of you have heard of, but using bits to represent characters, and then more importantly, certainly as well, more important, the number crunching, whether you do integers and how you or floating points and how you represent, choose complement for negative numbers and things like that. We're going to talk all about that. But for the purposes of this talk and this paper, microcontrollers use integers. This would be the number ranges you would talk about with integers, and floating points not discussed here, other than the fact that microprocessors can have a much larger range. Floating points, double precision floating points, you can go to 10 to the 308th power, plus or minus the number range, and super precision too with 64 bits of to use. Not all that's the precision, but still. Now, these code examples are not for this class here. These are code examples in assembly language comparing microprocessor to a microcontroller. So if you want to learn more about that, take one of my advanced classes. Now, it used to be in 333, now it's going to be in this merged version of a couple courses. The limited 8051 instruction set also contributes to many lines of code, the many lines of code needed. So this assembly language, this all assembly language, right? Direct one-to-one corresponds to machine code. A microprocessor has these more powerful instructions, so you need less lines of code, but the cycles it takes to execute them, and that's a key thing, are more here. And so you have very low cycles time to execute, but you need more lines of code. So it's a headache to program it. But with that headache comes more control. You know absolutely what's going on. You are controlling the bits everywhere, all across the silicon, at the ports, talking to everything else. You're interfacing what's poking at you for interrupts, or if you're polling for things, waiting for somebody to tell you something from the outside world, sending flags, semi-foreign communication signals, real-time operating systems, robot control, fast, high-speed military applications. You want to know what's going on down at this level, but not for this class. Just the yellow. And then this would be something more in line with what I might ask students here. Well, all the yellow is. Probably the most defining characteristic of microcontrollers is the on-chip circuitry for interfacing with external devices. This includes watchdog timers, waiting for some device to react, analog to digital and digital to analog converters. In this class, we talk all about, I have a whole lecture on digital versus analog waves and sampling things, and the math that's different in the analog world and the digital world. The natural world is mostly analog. It's almost entirely analog, but our computers are digital, so we got to go back and forth. And so you have these ADCs and DACs for conversion. Pulse width modulation is for driving motors, a special signal coming out. And then many counters for timing and control. You typically don't find these kind of things in microprocessors. The microcontroller is best suited for embedded single chip computer for controlling peripheral devices. Microprocessor best for high-speed general purpose, high precision, math-intensive stuff, multimedia, everything else. Or programming, which makes use of large address spaces, right? However, as the number of features that can fit on a single chip increases, the microcontroller starts to look like a microprocessor, but still ways off and defeats the whole purpose if you start doing everything in one package. We're not there yet. I mean, at some point when well, Moore's law, as we know, we're bumping our head up against that. When we're hitting the atomic diameter, trying to get smaller, we're already going as fast as we possibly can, and the speed of electricity is about a third the speed of the light, and we're switching order of magnitudes at that speed now. So, and the 3D transistors isn't going to save the day, or wafer scale. Not when you're trying to double something every short period of time. And then there's other stuff here too, including labs, things we build in lab courses. Okay, so let's go back now, get a context here. So we just did this one here. I'll come back. The Zoom will be saved as an MP4, I'll download it, and then I've got to upload it back to YouTube. But I'll VPN into my office machine, and then I connect to the web server, and I port the MP4 over there, so it'll be on the web server, and then I upload to YouTube. And I imagine I'm 60 years old. I'll teach at least 65, probably 66 now. But it's nice to think that things will stay on the web server here at Town College for another couple of decades after that. But if not, YouTube is supposedly permanent, and this whole course is going to be on there now. So microprocessors, microcontrollers, again, some of this we talked about up here, in this up here. And so, and that's all on YouTube and linked to from the syllabus too, off of my website, if you want to find that. Right. So let's see, stop sharing now. Okay. Stop recording now.